That's okay. Yeah, we can go ahead.
All right, so question number one. Your overall design of your rocket contains multiple complex electronic systems. How did the team determine that all the electronic systems would successfully function simultaneously and were mutually compatible under actual flight conditions? And EMI, EMC system testing in particular.
All right, so I can take that question. So the main electronic systems I believe you're referring to are both the payload, the deployment avionics bay, and the universal flight computer. I will throw the universal flight computer down to Alex to answer that question. For the deployment avionics bay, we used commercial altimeters for that. We just made sure that we really over-designed that avionics bay to make sure that the structural components were able to withstand any of the G-forces during the launch, and that all the wiring and everything was solid and secure. We have had success. Now, this isn't an answer saying we're doing this because, it's the way we've done it before, but we have had designed multiple deployment avionics bays in the past that have been able to withstand high G-forces. So we iterated upon those designs just to make sure that the materials used for those designs would be able to withstand a rocket launch. I'll throw it down to Alex to talk about the universal flight computer.
Yeah, so as far as the UFC goes, one of the big things about that is that none of the components on board the UFC are flight critical. So in the event, if the UFC electronics did completely fail, although that would be unfortunate, the flight would still be able to continue as expected, and it wouldn't affect any of the other flight things that need to happen during flight. As far as testing and making sure that the complex electronics and everything can actually handle the launch, we have a couple of mechanisms inside the UFC that I don't have too much time to go into detail, but we implement CRC and error correcting and detection codes in our communication protocols to see that if there is any miscontact between electrical communication lines, we can pick that up. And we just have constant onboard data logging so that if something does go wrong, we're able to look at that on the ground and hopefully iterate over and correct that flaw in our design for next year.
And Jacob, would you like to answer this for the payload?
Yeah, sure. So the payload has a couple different systems, electronic systems that it uses. For actual flight control, there is a Pix Racer autopilot that is used. And then also alongside that, for things like recovery and parachute deployment, there are a variety of commercial systems. So if at any point the Pix Racer doesn't know what's going on, or if it gets too low or anything like that happens, ultimately there are commercial systems there that are going to end the flight safely with parachutes and stuff like that. Otherwise, we trust the Pix Racer system to be able to control the autopilot and fly our little drone there just fine.
So just to sort of follow up a little bit.
I should say, my name is PJ and Alex.
Go ahead.
Actually.
No. It sounds like a lot of what I just heard talked about if you had a failure, that you've designed in some redundancy, you've designed some safety features. I guess specifically the question is, have you done pre-testing to try to convince yourself that you're not likely to have a failure in terms of any kind of electrical interactions?
I'm having Wi-Fi issues on my end, apparently. Could you repeat that question?
Well, I was saying a lot of the conversations you talked about, if we had a failure, here's how the system will recover from it, or that it'll be safe. I know structurally you talked about like wiring and structure, or that the structure was built soundly. Electronically, though, have you fired up your entire system with all of the systems operational to check within proximity to each other that you don't have any kind of electrical interference issues or things of that nature? I don't, maybe you answered it, but maybe I didn't catch that.
Yeah, we did so at our test flight that we had last weekend. We fired up the UFC and the deployment avionics bay. And the payload, we had to go without electronics for that one, just because we had to convert that to ballast mass to get below the altitude ceiling. But we're confident that the electronics from the payload would not have interfered with the electronics in the deployment avionics bay. The deployment avionics bay also has 3 altimeters, and they did not interfere with each other.
Okay.
I can also speak a little bit. Oh, go ahead.
I was just going to say, what builds your confidence? The fact that you flew successfully or test results?
Flew successfully, and just like test results too. We've flown this configuration before, and we haven't had issues with electronics interfering with each other, and this was the same last weekend.
Okay, Alex, I interrupted you. Did you want to jump in? Sorry about that.
No problem. I can also speak to the UFC. Our test flight last weekend was one of the first. That was the first time we actually were able to put the mechanism in a rocket, and we're still looking to get the data and analyze that. But one of the big things we wanted to make sure test to suss out some failure modes is the vibration stress on the electrical connections. We were hoping to have a fully assembled flight computer assembly and put that on a sieve or some kind of vibration shaker before we had launched. Unfortunately, due to COVID, the lab facilities containing any of this stuff were not available to us. So unfortunately, we had to test with our test launch for any vibration failure modes amongst the electronics. But there were some degree of testing plans for that.
Okay. I think I'm going to go ahead and go on unless anyone had any other follow-up. So the next question is, max Q is a critical point during the flight of a rocket. It's the point at which the airframe undergoes maximum mechanical stress, directly proportional to the square of the velocity. Maximum velocity is usually reached at motor burnout. On page 42 of your technical report, you indicate that max Q is reached at approximately 7.2 seconds after launch, but your motor burnout occurs at 6.9 seconds. At which point the rocket should be slowing down? Can the team walk us through that analysis? And I can repeat any of that. That was a lot of words, but hopefully that made sense.
I will. I'll actually forward that to Tyler because we were able to have a static motor fire, test right as we were submitting our final report. So I'll let Tyler handle this in terms of motor burnout time and everything.
Yeah, so ultimately the discrepancies there come in how we do our simulations. So with any actual motor test, you're not going to get the exact thrust curve you'd get in a simulated thrust curve when it starts and it ends. You have things called activation time versus your actual burn time. And the discrepancies there are within the slight amount of, I guess, pressure thrust you're getting from the end of burnout compared to the actual simulation. I think our slight discrepancies between burnout and max Q are it just kind of depends on which thrust curve you choose to use. So your burn time is actually not exactly how long your motor is burned, as there's still some happening.
Okay, so what defines burn time? You're saying, is that somewhat
arbitrary? How we define burn, it's burn time and activation time. Our activation time we classify as 10% of your maximum thrust. Okay. But if you were to actually look at a burn curve, you're trailing off for a while. So if we were to actually do the full thrust curve, it's a 20-second thrust curve. But if you were to actually do your activation time, it's 6.9 seconds roughly. But depending on how you define it, there's no actual definition. You could go all the way to anything you wanted to. So that's kind of how we defined it versus using the actual thrust data.
Okay. All right. Next question. You have a three-way redundancy for your chutes. What was the cost, benefit, and weight analysis that drove you to that solution? And specifically, what problem were you trying to solve from going from, say, the typical 2 redundancy system to a 3? And hypothetically, then you could say, why not, if 3 is better than 2, why wouldn't 4 be better than 3?
So the main reason why we went with that is, at some point, again, when you're adding additional altimeters, you just have to set the cutoff point somewhere. And the more altimeters you have, that's a lot of stuff you have to fit into an avionics bay. Those are more black powder charges that you have to integrate into the actual body tubes. So we just came to the conclusion that 3 is better than 2, but it's not overly complex. And we can also utilize 3 different altimeters with different battery requirements. So we just can although there's more fail points introduced, they're not critical in terms of if one fail point happens, well, the other one might not, because we're using 3 different batteries on 3 different altimeters, an AIM Extra, a Stratologger, and a Raven. So we just figured that that would be a safe solution in order to ensure that a rocket will deploy the chutes and that we will be able to have a safe recovery. Of course, and when you introduce more altimeters that can, theoretically, be a safer solution, it just introduces the complexity, and we do want to be able to get the rocket out. on the launch pad. So it was a cost benefit analysis between complexity and between safety factors.
Okay. Your two chute option, because you guys have flown before, I believe, right?
Mhm.
Did your two chute option that you've flown previously not have sufficient safety margin? Or I guess that comes down to what problem were you trying to solve?
I could maybe bounce it off a little bit. I'm the Caden Turner. I'm the recovery lead. We have flown our recovery system of a very similar configuration like this before, but really we have 3 altimeters just to increase, redundancy, and we weren't very concerned about the weights really. We're pretty close to, our 30,000 feet mark. So weight wasn't really a factor, and we could fit 3 altimeters into the avionics space-wise. So there really wasn't any reason, not to add a third avionics option.
Okay. I'll be curious, when you fly, it'd be an interesting report to compare all 3, just out of curiosity, see how well they perform compared to each other. So, okay, fair. That's fair answer. Next question. If I told you your mission flew, but it failed, what would you expect to be the most likely cause? And based on that expectation, what have you done to address the most likely failure mode?
I'm sorry, again, I'm having Wi-Fi issues. Could you repeat that question?
Sure. So if I told you that your mission flew but failed, what would you expect to be the most likely cause? And based on that most likely cause, what have you done to address that failure mode?
Just failed, like you just told us it failed. That's all we knew.
You're back in Minnesota and the team calls and said, it failed. And you'd say, oh, it must have been the blah.
All right, well, we have fully tested the motor and everything went well twice, so we know it wouldn't be the motor.
Mm-hmm. I would say it would likely be the parachute system. And that's not a dash in our recovery system. It's just that in past experience, we have improved upon designs, but we have had issues where parachutes have ripped in the past, and they've still been able to descend under chute, and it does slow down the descent rate. It's just that either the deployment speed is too high, so there might be tears in the parachute, so the landing might be a little bit rougher than if it was a perfect recovery. So that would be my intuition, and I'm sure Caden can bounce off of that, but we would just have to improve the durability of our parachutes.
Yeah,
and have you done that?
I'm sorry. Well, sorry.
Oh, I said, have you made improvements? And it sounds like you had concerns about your parachutes. What improvements have you made then?
So actually, so the main problem that we've actually had with parachutes in the past, especially with the main parachute, is tangling and twisting of the shock cord and stuff like that, which is had issues with deployment. We haven't really had any issues with our drogue parachute. So this year we packed the main parachute differently, as well as the shock cord. We daisy chained the shock cord to prevent tangling as much as possible when it deploys. And it appears that in our past test flight that it did not tangle. So.
Okay. All right. We're getting short on time. I got another question for you, but it's kind of a fluffy question. So we'll let you just talk for a minute or so. With COVID, there was presented many unique challenges to the competition. Can you briefly describe any unexpected opportunities and any unexpected challenges that COVID presented to your work and process this year?
Ooh, I have the perfect one. So we were briefly approved by the FAA to be able to fly up to 30,000 feet out of North Branch, Minnesota. And then they contacted us 3 weeks after we got the approval, and they're like, oh, actually this one FAA regulation is still in place, so we're revoking the waiver. So we still had to fly to 20,000 feet, but we wanted to make sure we got a test flight under our belt. So we had to make some very quick last-minute adjustments to our SRAD motor in order to ensure we did not go over the altitude ceiling. And that essentially consisted of taking out a grain and decreasing the burn time, decreasing the impulse. And it worked. We were able to stand at 20,000 feet.
You did that in two weeks. You did all that with COVID.
Yep.
Nice. Very nice. Okay. Any other thoughts? Otherwise, I think we'll we probably say, I apologize. I think I apologized before, but I'll continue to. 15 minutes is not much time. So we're looking forward to next year. We'll see you out there at the range, and we'll have all kinds of time to talk.
Awesome.
Exactly. Thank you, Todd, Steve, and Chris. We look forward to seeing you guys next year.
Thanks.
We'll see you next year.
Thanks, guys.